Okay. Good evening. My name is Anvesh, and today we'll be going over the solutions for the assignment of week 8. Uh, let's get started. So, let's get started. So, this week goes over the Rayleigh-Plateau instability and how the different modes such as uh, varicose and sinuous mode emerge from a filament, and basically how these instabilities grow and which of them are destructive growths and which are stabilizing growths. So without much ado, let's get started. Okay, so first question. In the discussion of the Rayleigh-Plateau instability, all normal modes are divided into two distinct categories: the sinuous mode, and the varicose mode. What mathematical reason allows us to make this distinction? So, solution. So, initially governing equations, then first, initially the governing equations are non-linear as they have terms like u dot del u by del x or u square by r and terms like these. So basically, these terms are neglected primarily due to the fact that we write expressions for only the perturbation velocity. So we essentially write the equations for only the perturbation velocity. Therefore, perturbation velocities being small as the displacements or perturbations are small, and therefore these non-linear terms can be neglected. So once these are neglected, governing equations are linear. Therefore, once they are linear, mathematically speaking, what is the proposition of? So first statement is true. So basically, the solution u can be written u sinuous plus u varicose, and this will still satisfy the solution. So again, we have that the linear. So once these terms are neglected, the governing equation becomes linear, and the sinuous and varicose mode are orthogonal to each other. This simply implies that these are independent of each other, and these come from different velocities which are perpendicular to each other. So therefore, third option is also correct. Therefore, we have option D is correct. All of the above is true. So now we have the next question. So the next question says this: consider a quiescent water filament of diameter 4 mm which is perturbed by a wave of wavelength 6 mm. Which of the below statement describes the balance of forces for a perturbation of this wavelength? You can assume the filament to be inviscid. We have diameter is 4 mm. We have lambda wavelength to be 6 mm, and fluid fluid is inviscid. Fluid is inviscid. So the fluid is inviscid. Therefore, now we have this. Okay, once wait a second. So we'll continue. Okay. So fluid is inviscid, and therefore, the condition that we already know a priori is that if lambda is greater than 2 pi r naught, then the filament is unstable. So this implies 2 pi 2, which is equals to 12.566 mm, and we know lambda is 6 mm. Therefore, therefore, lambda is less than 2 pi r naught. Therefore, we can say this implies the filament is stable. This simply means that the surface tension and inertia balance each each other exhibits filament exhibits undamped stable oscillations. So the correct option is C. The correct option is C. So moving to the next question. The analysis of the Rayleigh-Plateau instability discussed in the course is an example of spatial instability, temporal instability, spatio-temporal instability, or azimuthal instability. So the Rayleigh-Plateau instability we generally write R. Okay, long time. R is a function of z comma t, and which is equals to r naught plus a small term epsilon times e to the power omega t plus I k z. Therefore, we can say that Rayleigh-Plateau instability is a temporal instability. In the analysis of the Rayleigh-Plateau instability, we assumed the filament to be stationary. What assumption allows us to justify such a simplification for a falling jet? The shape of the falling filament can be approximated as a cylinder. The surrounding gas is passive. The velocity profile inside the falling jet is approximately useful. So, so first we assume that the velocity in the profile. So one of the first assumptions is that the velocity profile inside the filament is approximately uniform. This implies that the jet is falling with a uniform velocity v, and the same velocity is of the viewer that is being moved along the filament. So this is also known as a Galilean, which is Gallun transformation. Galilean transformation, and this allows us to move from a stationary reference to a moving reference without change in the solution. Therefore, the option C and option A are correct. And in this analysis, we also assume the surrounding gas to be passive. So, therefore, the answer to this is D. So the next question in the course, the growth rate of the Rayleigh-Plateau instability was derived assuming that the dominant modes to be the varicose mode. One can repeat the analysis and obtain the dispersion relation for the sinuous modes. Which of the below expression represents the dispersion relation for the sinuous mode? So the expression for R is given by this expression. So we can say given R is equals to R naught plus epsilon plus epsilon e power omega t plus I kz plus I theta. So in this case, the governing equations are not axisymmetric. So, so the governing equation can be written as del u r by del r plus del u theta by del theta plus here 1 by r and then del u z by del z plus u r and r equals to 0. Then we have the momentum equation. Del u r by del r. Okay, not del u r by del r. It's del u r by del t plus u r del u r by del r plus u theta by r del u r by del theta plus u z del u r by del z is equals to is 1 minus u r square by r is equals to minus 1 by rho del p by del r. And the viscous terms are neglected. Similarly, we have del u theta by del t plus u r by del u theta by del r plus u theta by r del u theta by del theta plus u z by del u theta by del z plus u r u theta by r is equals to minus 1 by rho del p by del theta, and then there's 1 by r as well. And then finally there is fourth del u z by del t plus u r by del u z by del r plus u z by r del u z. No, here it is theta. Del u z by del theta plus u z del u z del u z by del z is equals to minus 1 by rho 1 by r del p by del z. So in these three equations, the quadratic terms similarly get some space here. So all of this will be negligible. So upon Then we have del UR by del T. Okay. Del UR. First equation is del UR by del R plus del U theta by del theta 1 by R plus U R by R plus del U Z by del Z equal to 0, which remains as it is. Then we have second equation, which is del U R by del T is equals to minus 1 by rho del P by del R. Similarly, third is del U theta by del T is equals to minus 1 by rho R del U del P by del theta. And then fourth will be del U Z by del T is equals to minus 1 by rho del P by del Z. So let us assume we have been given, it is given or given in the hint that R is equals to R naught plus epsilon e to the power omega t plus I k z plus I theta. So therefore, our assumed expressions, the variable separable assumed expression for u r, which is equals to r comma t. Okay, I'll leave this out, which is equals to u r e to the power omega t plus I k z plus I theta. Similarly, u theta u theta is equals to br e omega t plus I k z plus I theta. WR plus e to the power omega t plus I k z plus I theta. And similarly, pressure is equals to PR e to the power omega t plus I k z plus I theta. So these are the assumed variable separable form. So substituting this into the first equation, we have del u by del r plus u by r plus iv r plus I q w is equals to 0. This implies first one. So if we substitute, this is the first equation, then we have omega v is equals to minus 1 by rho 1 by r I p. Then we have omega u is equals to minus 1 by rho del p by del r. And then finally we have omega w is equals to minus 1 by rho I k p. So first so now we have equation A and B. This implies using A and B equations we get minus IP by rho which is equals to omega VR. This implies IP by rho is equals to omega W by K. This implies RV is equals to omega by K. This implies V is equals to omega W K R. So then we have all the three equations where V is equals to minus I P rho omega R, W is equals to minus I K P by rho omega, and U is equals to minus rho W del P by del R. Substituting all of this back into the continuity equation, into continuity, substituting all of this in back into the continuity and simplifying, you we will get r square del square p by del r square plus r del p by del r minus 1 plus k square r square p is equals to 0, which is a form of Bessel's equation. Therefore, the solution can be written as ER is equals to C1 I1 KR plus C2 I2 KR. So let me get some more space. So as K goes to 0, okay. As r goes to 0, I2 kr goes to infinity. Therefore, to satisfy boundary condition, C2 is set to 0. This implies PR is equals to C1 I1 KR. So from here, once we find P, we have we have we have U, which is equals to minus 1 by rho omega C1 K I dash 1 KR. V is equals to minus I rho omega C1 R I1 KR, and W is equals to minus I R omega K C1 I1 KR. So these are the values of the three components of velocity. So these are the three values of continuity. Now, using the kinematic condition, we get the growth rate, which is condition, kinematic condition, which is equals to del R by del T is equals to UR at R is equals to R. This implies epsilon omega is equals to UR by R is equals to R. Now, this implies epsilon omega is equals to minus 1 by rho omega C1 K I1 dash K R naught. The dynamic condition on the interface is given by del T is equals to gamma 1 by R1 plus 1 by R, where R 1 by R1. One of the radius of curvature is R naught. Then 1 by R2 is equals to given by epsilon k square E omega t plus I k z plus I theta. Then P R at R equal to R naught is equals to gamma epsilon E omega t plus I k z plus I theta, which is equals to C1 I1 k R naught is equals to minus epsilon gamma k square. This implies we find the C1 value, which is equals to minus gamma epsilon k square by I1 k R naught. We mark this equation kinematic condition as star and replace substituting C1 value into the star equation. Star equation, then we get this implies omega square is equals to gamma k cube by rho I1 dash kr by I1 kr. Therefore, the correct option is, after the long analysis, we find that the correct option is A. Then correct option is A. Now moving to the next question. So now in the next question we have what is the reason for neglecting the non-linear terms in the governing equation of the Rayleigh-Plateau instability? So as we just saw in the above question, so for example, del UR by del T plus UR del UR by del R plus U theta by R del U theta by del theta plus UZ by del UR here R UR by del Z is equals to minus del P by del R. So in this equation we have terms such as UR into del UR by del R. So in these type of situations, our primary equation will be U, which is equals to U main, which is the main U velocity plus U fluctuation. So according to the Galilean transformation, we can subtract the U main and only have the U fluctuation. And generally, U fluctuation is very small. Therefore, this enables us to neglect non-linear terms. So therefore, we are able to neglect the non-linear terms. We are dealing with perturbation velocities to be more precise, and therefore we are able to neglect these. So the correct Option is A. I'll briefly take a break of 5 minutes and get back. So, So let's look at question number 7 now. So question number 7 and 8 are connected, and the question says that glycerin is being dispensed through a tap of 5 millimeter diameter. The filament ruptures when the most dangerous mode perturbs it, causing the filament to break up into droplets. What is the growth rate for this mode? Assume the following parameters for glycerin: viscosity, density, surface tension, and gravity. So first let's write down what is given. Its viscosity mu is equals to 1.4 Pascal second. Density rho is equals to 1260 kg per meter cube. Gamma is equals to 0.065 Newton per meter, and gravity G is equals to 9.81 meter per second square. So since the filament is being perturbed by the most dangerous mode, which is the varicose mode, we know the growth rate W max is given by the square root of gamma by rho r naught cube. So it is given that the diameter D is equals to 5 mm. This implies the radius r naught is equals to 2.5 into 10 to the power minus 3 meters. So we have here it is 0.34, which is equals to 0.34 into under root 0.065 divided by 1260 into 2.5 into 10 to the power minus 3, which is equals to 19.536 per second. So this is the omega. Once we have the omega, then we have so we have the omega. So what is the growth rate? So therefore the growth rate comes out to be C, which is 19.5 second inverse. So correct option is C. So the next question says, what is the approximate diameter of the droplet formed? So for solution solution 8, we have the same parameters, and for the same parameters we have, so the filament breaks into, not the filament which breaks into breaks, this is the center line, then it breaks into, this is given by R naught, and then therefore we know lambda is equals to 2 pi R naught, and therefore we have R naught is, of lambda, and therefore we have one droplet takes up the volume of the filament that breaks up into the dominant mode. Therefore, we have pi r naught square lambda, which is the volume of the cylinder, which breaks up into a single droplet, which is equal to 4 by 3 pi r drop cube. Therefore, r drop is equals to pi cancels pi 3 by 4 into lambda r naught square into 2 pi r naught divided by just 4 by 3, and then we'll take the square root. This is equals to 3 into 2 into pi into r naught cube, which is equals to 2.5 into 10 to the power minus 5 whole cube divided by 4, which is equals to 4.19. Therefore the answer is B, as the double of 4.19 is equals to 8.4. This is the radius. Draw. Draw. So therefore the answer correct option. So finally the last question. Consider a varicose perturbation of a filament shown in blue. If the filament is stable, that is the perturbation decays with time, which among the four velocity profile accurately describes the shape of the radial component UR. So we are concerned with UR. These are plots of UR, 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 UR. Theta. So we have the radial component UR. So first let us get some space. So space. So we are given, okay. So let me So let me redraw the diagram. So we have part in the diagram. So we have a shape like this, and to stabilize, we want the shape to go into a cylinder. So for this to happen, we want the velocity to go from the thicker parts into the thinner parts. So we have something like these. So we see that here the radial velocity is negative and towards the center. So UR is pointing like this. And situations where there is a necking, there the UR is positive. So both at the top and bottom, the UR is negative, and therefore UR is both negative here and here. And this is the only option that satisfies this situation. And also the in the middle region there is a positive UR. Therefore, the second option is correct. And just for clarity, I'll redraw the. So if I copy this, so this is the position Z, and this is the magnitude UR. So it is negative when we are at the top, which is negative here, 0 comma 0. And then as we move to the thinnest part, we have a, okay, I'll draw this curve in green. So we have minima. So we have the negative value at the top where the filament is the thickest. And as we go to the middle portion where it is thinning, we have a positive UR. And then again at the bottom, we have a negative value. So this is positive, this is negative. Therefore, the correct option is B. So here we end the questions. So in the last class, there was some confusion regarding the final question. So let's look at that. VK. No, not VQ. it's 7. Okay, so the final question was this. So this is the week 8, question 9 and 10. First, let me just close this. So once again, we recollect the question. We have a tightly fitted solid cylinder and is able to move along the axis of a long vertical tube with oil of constant viscosity mu, which is being pumped up at a volumetric flow rate q. So mu and q. The tube has a radius a plus h, whereas where h is much smaller than a. The cylinder has a weight w and specific dimensions shown in the figure below. Using the lubrication approximation, derive an expression for the volumetric flow rate q required to keep the cylinder stationary. Assume that the pressure is uniform both above and below the cylinders, and neglect buoyancy effects. So this was the question, and in question number 10, the we use the same. In the previous question, what is the pressure difference required to maintain the cylinder stationary? So we have two questions. We had uh, we had gotten the answer for the question number 10, but let's see how the question needs to be solved. So in this, we have the figure redrawn here, where there is a volume flow rate Q from the bottom and weight W of the solid cylinder, and the radius as shown as 2a for the block and a plus h for the uh, cylinder entire cavity of the cylinder. So then we take the axis to be 0, and the point at which the cylindrical block ends is x equal to a, and the wall is equals to x equal to a plus h. So the coordinate system as x, y, and z. So then we solve the equation. So basically we write down the continuity and momentum equations for the gap. So here we take the full 3D equation, and therefore del dot u vector is equals to del u by del x plus del u by del y plus del w by del z, which is equals to 0. So what are the assumptions made? The assumptions are the no slip at both the cylinder wall and the external outer cylinder wall. The thermophysical properties are constant, and if we carefully notice, then the upward velocity w u z is equals to w is only a function of x, is only a function of x. So therefore, w is a function of x. So from solving the continuity equation, we get that del u by del x is equals to del v by del y is equals to del w by del z, which is equals to 0. So therefore, the only way w can be is to be only a function of x. Why is it not a function of, why is it not a function of y? Okay, now let's look at the z momentum equation. So if we write down the z momentum equation, some of the terms like del omega by del t, u, v, del w by del z goes to 0. And similarly on the RHS, as w is not a function of y and w is not a function of z, both of the terms cancel out. So why is that? So w is not a function of y primarily because there is no possibility of having a rotational component. Therefore, the y component is also 0. Subsequently, if we write down the equations like previously, we can reach the point till here, same as shown before. The only difference being C1 and C2 need to be found out using the new boundary conditions, that is at x equal to a, w is equal to 0, and x equal to a plus h, w again goes to 0. So again substituting both of the boundary condition into the equation, we will get the value of C1, which is this, and C2, which is this. Substituting back into the equation, we get the expression for W. Once we have the equation for W, we again balance the forces, that is W is equals to the force of uh, viscous is balanced by the viscous force and the difference in pressure. So it is basically pressure into area, delta P into area. So substituting that, we have this equation like so, and using the velocity W, we get the viscous force. So once we have the viscous force and we substitute everything else, we get the pressure difference to be Pi minus Pe is equals to W by pi A into A plus H, which is this. This was also found to be same in the previous analysis where the center was shifted. Basically, the center was here. So upon solving that, we get the same pressure difference. So now comes the part where we weren't able to get the solution. So for volume flow rate Q, the expression is integration of 2 pi x, which is a cylindrical ring which is of dx. and radius x. So the expression is 2 pi x dx. 2 pi x dx is the area and wx is the velocity. Therefore, this gives us the volume flow rate. So once we already know wx, no. So we substitute wx into the equation and integrate from a to a plus h. So upon doing the exercise, we'll find the volume flow rate Q to equal to W by 12 mu L into A plus 2A plus H divided by A into A plus H into HQ. Once we get this, we cut the values. We cut the values and then we have the final expression of Q, which is equals to Q is equals to W by H, W into H cube by 6 mu AL. Therefore, the correct option is B. So, in the question, we have B. So, this was the last time we had basically taken the center from the wall of the cylinder. From here onwards, we have taken, but such an analysis gives an incorrect solution as the distance of, if we take the center from here, the length of wall from one side will be h and the other side it will be h plus 2a. Therefore, this breaks the symmetry and the answer is incorrect when taking a cylindrical strip. This needs to be x in all the direction. Therefore, this was the error made in the last analysis in the last time. So this is why it was the the answer was incorrect. So this is the correct solution procedure for the question in the previous week. So I'll end here and
Minus 1 sir, 3.5.